Alright, so this is my video explainer 6 for homework 3, and the problem I chose is 12.43, which gives us this scenario. What is the angular momentum vector of a 2 kilogram, 4 centimeter diameter rotating disc that's shown in figure 1, but we don't have to worry about that, and give your answer using unit vectors. Unit vectors, alright, and so you're going to express your answer in kilogram meters squared per second, of course. And enter components of momentum separated by commas. So in this case, because there's three axes, we're going to have Lx, Ly, and Lz. And I mean, there's probably only going to be one axis, but really what's important is just determining what's z, what's x, and what's y. So then when we do find that direction of the angular momentum using the right-hand rule, then we can figure that out. And so we have x over here is this axis that's going through the center directly, and then we have z, which goes up and down, and then we have y, which goes, I guess, horizontally through the cylinder. All right, and so what we were given, so that's what this drawing is for. It really is supposed to represent things. R equals 0.02 meters, because we get 4 centimeters, convert that to meters, and that works. All right, so our drawing here really tells us what we need to know. We have these three axes, and we want to find the angular momentum given the way that it's rotating. This isn't necessarily too hard to do because we just have the right-hand rule. And so if you make your hand sort of flappy in the direction of this arrow, the only way you can do that is to have your thumb pointing that way. And we know that that direction corresponds with the x. More specifically, it's the negative x direction. And so we should get an x. Our momentum should be in the x direction, and it will probably be negative in all likelihood. Or we know it should be negative, and it will be. So what we're going to do is we're going to solve for L. We have that in our little toolbox. L equals I omega, moment of inertia times omega. We have the radius, we have the mass, we have everything we need. We have omega, we even know the moment of inertia of the cylinder, which we're using a lot these days, 1/2 mr squared. And so let's do that. Let's find let's find the moment of inertia. So 1/2 mr squared equals, in this case, we don't really have to do any extra solving because it's not, the axis isn't shifted, 0.02 meters squared. And what that equals is a pretty small number, 4 times 10 to the negative fourth kilograms meters to the negative 2. Okay, so we have our moment of inertia. Next up, the other component of angular momentum is omega. And we're given omega, but it's probably best for us if we convert it into radians per second, just because that's the baseline unit for that number. And so 1 revolution is 2 pi radians, and 1 minute is 60 seconds, which ends up equaling 20 pi radians per second. And so now we really have everything. This problem is pretty straightforward. Now we just have to multiply those two things that we just solved for. And so we get is L equals moment of inertia times our angular velocity. And so then we get 4 times 10 to the negative fourth kilograms per, times meters squared, but I, for some reason, like writing it that way. And then multiplied by our angular velocity, which is 20 pi radians per second. What we end up getting is 0.025 kilogram meters times meters per second, or 0.025 kilograms meters squared per second. Yeah, okay, I don't know. I mean, that just looks cleaner to me. But that's our answer. But the direction is determined, again, by this little right-hand rule. This is supposed to represent the right-hand rule, but you should do it yourself. Curl your hands. Look at the picture here. Look at the way that the arrow is pointing, and make your hand grab the axis and have your hand wrap around in the same direction, same way that if you drew a circle, but your arrow is like the tips of your fingers, then do that, and then see which way your thumb is pointing. It's into the screen or in the negative x direction. And so our fully written out momentum is Lx, Ly, Lz equals, since it's only in the x direction, in the negative x direction, negative 0.025 kilogram meters squared per second. And then it's 0 kilogram meters squared per second. And then 0 kilogram meters squared per second. And that is our answer. So for this problem, yeah, it's pretty straightforward, but just remember to use the right-hand rule. When I first did this problem, I got the right answer, but I didn't have it in the right direction because I was a little confused about that sort of vector, well, not net unit vector notation with angular momentum. I don't think we'd study it in class. But then, right-hand rule, okay, that makes sense if I just wrap my hand. Yeah, so that's a little tricky. And then, of course, just remember that angular momentum is moment of inertia times angular momentum, angular velocity, very similar to linear, just angular. And yeah.